All right, let's get started. First of all, thank you for taking time to join the session on architecting for high availability. It's great to see so many of you. Thank you very much. My name is Attila Narin. I'm with Amazon for about 8 years now. I'm currently based out of Europe, where I'm part of the European team at AWS. Specifically, I'm part of the solutions architecture team. As part of that team, we help customers be successful on the Amazon platform to build systems that are scalable, fault-tolerant, highly available, secure, and so on. And today in this talk, we'll be covering some of the concepts that we talk with our customers about regarding architecting for high availability. There are 5 points that I'd like to talk through today: designing for failure, multiple availability zones and how to properly use them, scaling, self-healing, and loose coupling. And what we're going to do here is we'll actually build a system. And by applying these 5 best practices, we'll end up building a system that is highly available. Now, the first point I'd like to make is that there are 2 groups of services that AWS offers. On the left-hand side, you see the services that are inherently fault-tolerant, scalable, and highly available. We heard Alyssa Henry talk earlier during the keynote how S3 does some of the heavy lifting behind the scenes in terms of dealing with issues, so you don't have to worry about it. So these services are designed to be highly available. And by picking those and adding those to your architecture, you're basically taking advantage of all the work and innovation that Amazon is doing behind the scenes. Now, on the other hand, there are also services that can be used to build highly available architectures, but you'll have to use some of the tools and features that those services provide correctly in order for those to be highly available. And we'll talk about some of those right now. To get started, we'll use Amazon EC2 and Amazon RDS, our relational database service, and Amazon Route 53 for DNS to start building our very simple system. So here we go. We'll take EC2 to host our web server. We will use the relational database service, which makes it really easy to manage and provision databases in the cloud, and we'll use that to set up our database. Next, we will use an elastic IP address that points to the web server. Elastic IP addresses have a couple of features, and the one that's relevant here is that you can actually map an elastic IP from one instance to another automatically. So this is quite interesting and important if you want to work around failures, which we'll see in a second. And lastly, we'll use Route 53, our DNS service, to resolve, in this case, www.mywebsite.com to the elastic IP address. Now, at this point, we want to start applying the 5 points one by one. Designing for failure. Let's jump into that. And this morning we heard Werner Vogel again use the famous quote, "Everything fails all the time." And it's just such an important point to keep in front of your eyes. Disks can fail, power units fail, applications have bugs and they go down, there are memory leaks, all kinds of things that can happen. So what we want to do is really look at your architecture and your system and see where are the single points of failures, and then actually try and avoid them. Obviously, if your system has a single point of failure and that system goes down, or that single point of failure goes down, your entire system is down. And then really assuming everything fails and work backwards from that and anticipate how you would guard against some of those failures and how you would remedy that in seamless ways. The goal really is to make sure your application and your system continues to function. And this is internet time with the increase of mobile devices, folks are connected. You just don't know how many people will join the party and will come to your application and come visit your site. So the last thing you want to do is when there's high demand, that your system is not available, or that if there's a failure, your system is not working. And in the past, you might have been worried that nobody comes and uses your application. Today, you want to be ready that everyone out there comes and visits your system. So let's go back to what we have built so far, and let's look at what would happen in an isolated failure case. Let's assume the web server has crashed. Let's say it's a memory leak in the web application. I'm sure many of you have encountered this in your careers, and the system is down. With AWS, since all of these are programmable components, what you can do here is basically launch a replacement instance, which is now hosting a new web server, and point the Elastic IP to this new server. So your system is back up and running, and it happens transparently to your clients. So that's a very basic example of how to deal with failures. Now, Amazon EBS is another service I'd like to introduce you to. Oftentimes, you want to take state with you from instance to instance if there is a failure. And EBS, or Elastic Block Store, gives you network-backed storage volumes whose lifetimes are independent from that of an instance. What that means is if an instance fails, or if you no longer need an instance, you can shut it down, but the data on your EBS volume will still be there. So you can move it to another instance as you wish. Let's take a look how the architecture is when there's an EBS volume attached to the web server. If there's a failure now, and we do the same thing, we launch a replacement instance and remap the Elastic IP address, you see that the EBS volume is still there. And using the APIs or the console, you can easily attach this volume to the new instance now. So if you want to take forward any kind of application state, log files, or anything you might need, that's a good way to do it. Now, the next service I'd like to introduce is Elastic Load Balancing. In our system that we've seen so far, we really had a couple of single points of failures, and ELB lets you scale horizontally across multiple instances, which is quite important. So let's take a look how ELB will be inserted here. Instead of using the Elastic IP pointing to a single web server, what we see here is traffic is flowing through the Elastic Load Balancing service, and traffic is spread across 3 instances. So at this point, there is a feature of Elastic Load Balancing which is called health checks. And as you might imagine, what this means is ELB can be configured to check the health of the instances that is behind it. And if an instance were no longer to pass that health check, ELB is smart about how it directs traffic. It's really simple to set up. You can, this is a screenshot from the AWS Management Console. You basically pick the protocol, pick the port, pick the URI, and you can configure a couple of values around a timeout and the frequency of your health checks. And from there on, ELB will simply perform the health checks. Now, back in our architecture drawing, let's see what happens now when one of the servers go down. ELB will continue to send traffic to the good instances, but we'll have figured out that, hey, this instance is no longer available, or this web service is no longer running, and it will no longer send traffic to that once it detected that. It continues to check the health of the system, though, and when the system is back in operating order, meaning it passes the health check again, ELB continues to send traffic to that instance. Yeah? This very briefly was how we designed for failure of single system failures. In this case, we had a memory leak in the web service, and we showed how we can use Elastic IP address or Elastic Load Balancing to work around that. What we'll talk about now is how to architect for multiple availability zones. As we heard, there can be correlated failures, and using multiple availability zones correctly is super important. In fact, if you walk away with one takeaway from this talk, let it be this one, using multiple availability zones correctly. So what is an availability zone? Availability zones are distinct locations that are engineered to be fault-tolerant or insulated from failure in any other availability zone. Meaning, if anything goes wrong in one availability zone, it will not impact the system in another. And even if you look at availability zones themselves, they are architected such that there is redundant power, redundant connectivity to tier 1 transit providers. They're in lower risk floodplains. So these think of those as programmable data centers, are fairly well constructed by themselves already. And by using multiple of those, you really can build systems that are highly available. Let's take a look at the map. We have quite a few regions at this point. We have our latest edition in Sydney, which you can see here. And these are regions, and within those regions, we have these multiple availability zones. And what's important here is availability zones within the same region provide low latency and inexpensive connectivity, which is important because you need to be able to synchronize your application's data across these zones and prepare for, if there was any problem in one of the AZs, you need to have your state replicated over. Let's jump in. At this point, I'd like to introduce a feature of the Amazon Relational Data Service, a database service called multi-AZ. RDS provides quite a few useful features in terms of setting up read replicas and allowing you to scale up and down or adding storage volumes. But here, multi-AZ is important. Multi-AZ, in fact, let's jump into our architecture and I'll explain it here. In multi-AZ deployment mode, RDS will set up a replica database in a second availability zone. So here we see on the upper left-hand side the architecture that we have just built in the first availability zone. They're labeled A and B here. And in zone B, we have the replica, which is now synchronously replicated from the main database. So it's fairly easy to set up, in fact. Let's, oh no, sorry. First, we'll look at what happens when there is a failure. So when the main database fails, RDS monitors that and actually switches over and promotes the replica to be the new master, and the EC2 instances running the web server continue to have a database to talk to. Now, in RDS multi-AZ deployments, the design idea is that there always needs to be a second set of, data needs to be duplicated. So what's happening, RDS will set up a new replica of the database and starts synchronous replication once again. And the part, synchronous here is important because the moment something is committed to your database, it is committed into two places. Now, it's really easy to set up. It's as simple as going to the management console and checking the right option in the dialog. But underneath, imagine all the things that are happening in terms of facilitating the replication, monitoring for the time that you need to shift over traffic and so on. So there's quite a bit of things happening under the covers here. Now, we've seen how we can bring the database across multiple availability zones, but how about the traffic to our web servers? These are still in one AZ, like we've just seen. Now, the good news is with Amazon ELB, you can easily switch on the ability to send traffic to multiple AZs. Let's jump back to our architecture. Here we have what we have built so far. You see the database replicated across two AZs, but our instances are still all in the first AZ. So by enabling ELB for multi-AZ, we can build something like this. You see traffic is coming into ELB, and we're distributing traffic evenly across two availability zones, and each of the zones is running, in this case, two instances, and it's a best practice to run the same amount of instances in each zone. Now, this is the core architecture drawing that you really should take home with you, in fact, and make sure you use these methodologies in your system. In fact, this is how the vast majority of customers ensure that their system is highly available. For example, Nokia Siemens Networks, based out of Finland, this is what they do. This is how they ensure their system is highly available. Very critical. And yeah. All right, we talked about multiple availability zones and how to use them. In fact, I want to give a brief example of how not to use them. For example, it would be incorrect to just randomly spread your instances across AZs, or for example, even worse, put all your front ends into one AZ and all your app servers into the second AZ. That's not how you want to use them, because now you actually made things worse. The right way of doing it is to put isolated application stacks or independent application stacks into each zone so that if one zone fails, the system continues to run. So, if aliens were to come down from space and take out one of those AZs, your system continues to run out of the other AZ. So check that out. Next, we'll talk about scaling. Why is scaling important in the context of high availability? Well, if your system becomes extremely popular overnight, you need to be able to scale up and provision enough capacity to handle the peak demand. So elasticity is one of the key architecture patterns here that you want to embrace, and this is what the cloud is really good at. So you need to be able to scale up and be ready to scale up when you expect demand most, because your users will not be able to differentiate between your system not being available because there's a failure or your system not being available because there are millions of other users knocking on the door at the same time. Let's go back what we have built so far. We see our system across 2 availability zones. Now, I'd like to introduce you to CloudWatch. CloudWatch is a monitoring service for your AWS resources. In this case, we're looking at CloudWatch for EC2 instances. Here you get metrics like CPU, disk utilization, network utilization, and so on. And CloudWatch, in combination with our auto-scaling service, makes it really easy to scale up and scale down your EC2 capacity. Basically, you can configure these systems such that EC2 instances that, in this example, like we'll see in a moment, run your web server are added automatically based on, for example, CPU utilization. Let's jump in and see how this looks like. Now you can, back to our architecture, you see that these instances are now monitored by CloudWatch, and systems are running. What we will do is we add a auto-scaling group to basically manage these systems now. And as load increases, you'll see the servers are starting to run hot. CPU is running higher, and they are slowly maxed out. Now, CloudWatch is going to send CPU metrics to auto-scaling, and auto-scaling would have been configured to basically look at the threshold and the trigger that it needs to use, and then the auto-scaling policy will kick in where you basically tell it which image or Amazon machine image to go and launch. And at this point, auto-scaling will automatically provision additional web servers. Here we can see how these machines are starting, and note how the load balancer only continues to send traffic to the existing instances because it's communicating with auto-scaling, and it's doing its health checks. It's basically knowing that those instances are not ready yet. But the moment they're ready to take traffic, you see that load balancing will send traffic to now 6 instances that are equally spread across 2 zones. And you also see that the system is no longer running hot. So this example scales from 2 to 3 instances in each AZ, but we have customers who scale from 40 to 80 to 120 instances. So this is really configurable and flexible. Now, when the demand is going down again, you see that the systems are running cooler, and auto-scaling would be configured to basically take away capacity that is no longer used. So here, with 3 instances running colder, you could actually shoulder that load with just 2 instances, and it would save you money. So auto-scaling will first talk to the load balancer and say, look, stop sending traffic to those instances. I'm about to take them down. And it will then shut down the systems. The load balancer will continue to send traffic to just 2 instances. And we're back to how we were in the beginning. Now, auto-scaling is a good way to deal with unexpected spikes. We've seen that automatically adds capacity as needed. But it kind of depends on how quickly your image or your AMI is ready in operational state. Sometimes it might take a couple of minutes or even 15 minutes, depending on what you have to do on this instance or on this AMI to get it ready to be operational. So you might consider just having a little bit of extra headroom by just adding 1 or 2 instances just in case you have a couple of unexpected spikes. Now, for expected spikes, it gets even easier. Autoscaling has a time-based trigger that can be configured. And in a lot of cases, that's what customers will do. For example, you very well know when, for example, the Olympic Games in London started. It's no surprise there. You know, people know the day and the time. Or if you're building an application in support of a TV show, you know when that show is on the air, and you can scale up accordingly. Now, we talked about the front ends up until now. And I briefly want to make 1 or 2 points about the data tier. And actually want to go back to the slide I showed in the beginning. We offer quite a few services that are highly available and scalable and fault tolerant by themselves. So a really easy way to add, for example, a scalable storage system to your architecture is simply by using Amazon S3, and you don't have to worry about it. It will worry about the scaling and all these aspects of high availability. Or if you need a high-performance scalable database, you can use DynamoDB, and all these things are taken care of for you. So this makes it really convenient and easy to build really highly available systems. All right, this was the point around scaling. Again, autoscaling and CloudWatch can be used to scale up and scale down as needed. You can keep some extra capacity around. What's really important here, and you know, this talk will not go into a lot of detail here, but think about how you package your images or your armies so that they themselves get into a state where they are usable. Like Werner Vogels was saying earlier, you don't want to SSH into a machine in order to get it ready and running. You want to automate that, and this makes the assumption that you have built your system so that happens. This brings me to my 4th point, self-healing. Here we want to look at detecting failures automatically and recovering from failures automatically. Let's jump straight in. And remember how we talked about the ELB health checks in our first lesson and autoscaling just now? Now we're going to look at combining those. In our architecture now, we see what we have built so far. Remember, we have our web servers in the autoscaling groups, and we have Elastic Load Balancer configured to spread traffic across those instances. In this case now, when an instance goes down, the health check in combination with autoscaling actually does the trick here. It'll detect that the system is bad. Autoscaling automatically terminates the bad instance and brings up a new one. And when that system is up and running, the load balancer again spreads traffic across all instances. Now, here we show that we simply throw away the old instance. That's generally a good practice. It's often not very interesting to find out why exactly the system failed. However, you can very well keep that system around as well for debugging, or if you have that memory leak, try and understand how to fix it or where it happened. So that's also possible. So we've seen here that health checks in combination with autoscaling gives you self-healing systems. But at this point, I want to briefly talk about the concept of a degraded mode as well, because sometimes you just need more time. Imagine, for example, you have a problem at the data tier, and you need to restore your database from a snapshot, or you need to go and do something else that just takes longer. You want to buy yourself time. And one way of doing this is to switch your system into degraded mode. What this means is basically not every feature is fully functioning. Maybe some parts of the system are read-only, or maybe even the entire system is read-only, but it is highly available. If customers use their web browsers and come and visit your site, they will at least see something and not get an error response. So a really easy way to implement the degraded mode is to use Amazon S3's ability to host static websites, and then using Amazon Route 53 to basically shift traffic back and forth between the static website in S3 and your production system that we have just built. So let's go back to the drawing board here. Actually, no, first, I just want to show you a screenshot here of how easy it is to configure S3 for hosting your static website. You basically check a mark and tell it what the URI is, and S3 does the rest to host your static website. And static here means it's static from the perspective of the server. You can very well have some clever client-side scripting in there that still gives a reasonably good experience to your customers. Okay, now we're going to jump to the architecture drawing. Here we see how the record set in Route 53 is configured to send 100% of the traffic over to your production system. And you also see that the S3 website is in there, but the weighting is set to 0. That means that 0% of the DNS resolutions are going to S3 at this point. And if you want to go into degraded mode, it's as simple as shifting those weights around. So instead of sending 100% of the traffic to your production side, you would send all that traffic against the static side hosted in S3. And now you bought yourself time. Now you can go back and do anything you need to do to your system to get it back up and running. You could also, here in this example, I showed how to shift between your production system behind ELB and using a database like we built here and S3, but you could also have multiple systems around so you can switch traffic back and forth as you want to. Now, when your system is back up and running, you can either just, bring 100% of the traffic over, or you can also do this more gradually, in case you're not quite sure if you fix the bottleneck or if it's all working. So you can do it more gradually if you want to. All right, here we talked about self-healing. Again, the ELB health checks in combination with auto-scaling, and we talked about the concept of the degraded mode. The last best practice here is loose coupling. This is really a fascinating topic, and we could probably have a whole session on this, and I know Werner started talking about this in his keynote as well and showed some examples. Here I want to show some additional examples specifically around how to use queuing and buffering. Let's remind ourselves why loose coupling is important. Number one, or one benefit is about scale. You can scale the independent stages of your distributed system independently. So you can really use optimal capacity at each stage and change the amount of capacity seamlessly. Second point is these loosely coupled systems help you be more fault tolerant, because a failure in one of your stages would not impact or would not trickle through to some of the other stages. At this point, I'd like to introduce you to the Amazon Simple Queue service, SQS. SQS gives you a highly reliable, scalable queuing service in the cloud. So you can basically pass the messages from one area of your distributed system and pick them up somewhere else. So it's a great way to tie together loosely coupled or distributed systems. Now, here's an example of how a system might look like, and here is a media transcoding pipeline. And this example talks about media, but this use case is by no means limited to media. We see a lot of applications using these kind of loosely coupled background processing, e-commerce fulfillment, batch transactions, and so on. So yes, it's a media example, but please don't think it's limited to the media space. And here what we see, we have a three-stage process between receiving, transcoding, and when the transcoding is done, to publish and notify customers of the transcoded media file. Now, the way it's shown here is it's actually tightly coupled, because receive directly calls into transcode, which directly calls into publish and notify. Now, good and easy way to turn this into a loosely coupled system is by putting SQS in between those stages, so that when a file is received, it will go into the queue buffers it and makes that media file available for the next stage, which transcode. When you're done with transcoding, you put it into the buffer, and it'll go into the publish and notify stage. Let's go back to our architecture drawing, and this now has a couple of additional components. I'll describe briefly what we see here. On the left bottom is the system that we have built up until now. You can see the elastic load balancer spreading traffic across our web servers. Then on the upper left-hand side, you see we added DynamoDB to our data tier to have a highly scalable and high-performing NoSQL database. That's where we keep metadata. On the lower right-hand side, you see Amazon S3 for storage. So we have two buckets here, one to store the original media files and one to store the transcoded files. In the upper middle of this drawing, you see SQS. This is the queue. And now we have a set of worker nodes that are behind the queue, and they pull the queue for work. This is where the transcoding work happens. Now, I'd like to walk you through how the system operates by briefly following how a message comes in from the user and flows through this. So, step one, the user uploads a media file. It flows through the load balancer, through the web server, gets stored in S3, and you see a message entering SQS here. And at this point, we have a single message waiting in SQS. And you see a single original media file in S3. Now, the transcoding worker nodes in the background continually pull the queue. And once there is a message in the queue, one of the workers pulls down the message. It goes to S3, pulls down the original media file, and does its transcoding. When the transcoding is done, it uploads the transcoded file into S3 for storage. Now, this is the normal flow of the system. At this point, I'd like to introduce you to the concept of a visibility timeout. You can think of this as the time allowance a worker node has to process a message. And if within that visibility timeout, the worker node didn't go back to the queue and acknowledge that, hey, I'm done with this, I'm processed, the message goes back into the queue and is eligible again to be processed by other nodes. The advantage here is that if there's any kind of failure of the worker node, the message is not lost, but it gets processed by another node. Let's take a look at how this looks like in our architecture. Here again, we're at the stage where we have a single message in the queue, and you can see the 3 worker nodes in the background pulling the queue. Now, again, we have one worker node pull down the message, get the original file out of S3, but now, instead of completing the work, let's assume the worker node fails. And you see the message is still with the worker node at this point. The queue at this point will not know yet that the worker node failed, but it will the moment the visibility timeout expires. And clearly, as this worker node has failed, it will not have been able to go back to the queuing service and confirm that the message can be taken out. So what happens, actually here, a quick screenshot on how to set up the visibility timeout. It's as easy as going into the management console and adjusting the value shown here in the UI. And it's really, it's a time span. So here in this example, we have 10 minutes. This would work well if your transcoding step maybe takes 4, 5, 6 minutes on average. So at 10 minutes, you know that, hey, something is wrong, something failed. We want to start reprocessing the same message on another node. All right, here we're back. The worker node now failed, and the visibility timeout is about to expire. What we see now is that the message is actually back available in the queue, eligible to be picked up by another worker node. And you see the remaining 2 worker nodes, they continue to pull the queue and look for messages. In this case, it's a rerun of that same message. One of the other nodes picks up the message and would do the transcoding. Yeah? Next concept I want to introduce is buffering. Buffering really helps with unexpected demand spikes. If you all of a sudden have a lot more media files coming into your system that needs to be transcoded, that need to be transcoded, and this really allows you to scale the independent stages of your distributed system accordingly. So let's jump straight in and see how this looks in action. Here again, the architecture that we have built so far. You see a single user here, and now let's say your application is really popular and demand is picking up. This is, by the way, the architecture that a lot of our customers are using for this. For example, Vimeo is doing this for video files. Lots of other examples. NASA has a similar approach. This is a really common pattern here. So hopefully this is something you can try and introduce into your applications as well. So scale is picking up. We have now a lot of users, and look what's happening to the system. A lot more media files are being uploaded, a lot more messages are inserted into the queue, a lot more things need to be stored. So the system overall is just humming and firing on all cylinders at this time. So see, however, that messages are already piling up at this point. So the 3 worker nodes we have in the background are no longer able to keep the queue empty. So we have some buffering going on already. Now, since we have configured auto-scaling for our front ends, look what's happening. Web server capacity is increased, and even more users are being supported by the system, which actually leads to even increased ingestion of these media files that now need to be transcoded. And as with most things in life, failures happen at the worst time. So let's assume now we scaled the system even further, and bam, we got one of the worker nodes in the back failing on us as well. Now we're kind of in a bad situation here. Availability might start suffering because, as customers or users upload media files, they expect a certain responsiveness. They want to see that their media gets transcoded and that they get notified, and now it's just taking longer. Got quite a bit piled up in this queue at this point. So what can help us here is CloudWatch metrics for Amazon SQS. We have seen CloudWatch earlier, how it works with the instances by basically picking up CPU and some of those metrics. Well, for SQS, one of the metrics that is interesting is the approximate number of messages in a queue. And you can combine this with autoscaling, so that autoscaling basically watches the queue and adds and removes capacity based on how many items are in the queue. Here's a screenshot of the console. Here we can see that it's the approximate number of messages visible. Again, visible because of the visibility timeout. It could be that there are items in the queue that are not visible, that are basically being processed by worker nodes. But here we want to look at the visible numbers. And let's say we configure autoscaling for this now in the background. Autoscaling will now see that there's a pile of messages in the queue, and it will provision a bunch of worker nodes. And look at this. This is now really picking up the pace here. You see a lot of messages flowing from the queue service to the worker nodes, and you see that we are really making progress against transcoding these files. In fact, you see the number of piled up items in the queue go down quickly, and you see how we have a lot of additional transcoded files showing up in S3. So this is good. This is, your system is responsive again, and your customers can pick up the transcoded file quickly. And now that the number of messages in the queue has gone down again, autoscaling will reprovision capacity and basically bring in the number of worker nodes in the background. And this is really a nice example where we see 2 autoscaling groups that really balance capacity on the front end and in the loosely coupled back end here. So that's a good example of loose coupling in action here. All right, this concludes the 5 steps I want to go through, but I'd like to recap quickly just so that we really can remember and take some of these home. So first point was about designing for failure. Here we used Elastic Block Store and Elastic IPs to work around single system failures. We looked at how to use health checks and ELB. We looked at using multiple availability zones, but again, they have to be used correctly. Don't just randomly distribute your instances across AZs. Don't put all your front ends in one AZ and all app servers into another. You've got to build independent stacks of the system. We looked at how to scale up using autoscaling. This is critical. If your system is under demand, you want to be able to quickly add capacity as needed so that your end user experience is positive. So we looked at autoscaling and how to set it up in combination with CloudWatch here. We looked at self-healing, basically detecting issues and correcting them on the fly. And in fact, customers really have innovated on this dimension here. There is the Netflix Chaos Monkey, for example, that automatically injects failures into the system just so you exercise the self-healing ability of your system. That's a great best practice. Lastly, we looked at loose coupling. We saw how we can use SQS the visibility timeout to guard against failures of the worker nodes. We have seen how to use buffering to increase and decrease capacity of the system under demand. Now, remember your goal. Your system needs to continue to run. So using some of those best practices, please make sure your system continues to run. Yeah. Lastly, the point I want to make is it's really about choice. If you have a system that is, for development or testing or staging purposes, you might not need high availability. You can save some money. That's why some of those services like EC2 and RDS, they give you choice. If you have a production system, it needs to be highly available. So make sure you follow these 5 best practices and some of the other ones to make sure you have the right availability in place. A couple of resources. We have the Architecture Center online. This is where the solutions architecture team provides best practices. You find reference architectures there. You find some white papers there. Go there and read more if this is something interesting to you. We have technical articles as well. I'm sure many of you have seen the AWS blog. And we also have a series of podcasts which illustrate some of these concepts. Some related content specifically here at this conference. Shortly after 4 o'clock, we have 2 talks that are interesting and related to this. We have an intro to the Chaos Monkey. So this is a great way to learn more about the self-healing and how tools can basically help you build systems that are highly available. So if, go and see that one. We also have a session about scale, also at the same time. So this is about scaling mobile applications and web apps. If you're keen to, we also have hands-on labs, and there are 2 that are relevant or related to this session. There is lab number 4, which deals with scaling, and there's lab number 12 about loose coupling. And I'm going to be around later. I'll be outside the room after this presentation. If you have questions, we also have the booth with solution architects in the main room. We all would be very happy to help you talk through some of your questions that you might have.